Alrighty, welcome back to operating systems. Quiet day today. What's going on today? Exams or something? Midterms? Career fair. Oh, okay. Well, we get a riveting day of more operating systems then. So today, the kind of slightly review, slightly stuff that won't be tested that might be useful for you, that is relevant. So basically it's just kind of review. So there's some easy priority scheduling that's typically taught is something called dynamic priority scheduling. Might also be called feedback scheduling in some textbooks. We went over, having a scheduling algorithm, assuming a single CPU that can go ahead and it picks which process to run at any given time. So for this one, before we went up to round robin, we didn't see any concrete examples with scheduling with priorities, so this is an example of one, and this algorithm is what is setting the priorities. So like round robin, we use time slices, but unlike round robin, we're measuring CPU usage, and then what we do is at the end of a time slice, we dynamically adjust the priorities of processes. So we'll increase priorities of processes that don't use their time slice and decrease the priority of processes that use their time slice. So you can initially say how important your process is, but over time it will degrade, and then eventually a low priority process will be able to run. So in this scheme, easiest thing to do is to pick a lower number to mean the highest priority. Each process gets assigned some priority when it starts. Let's call it P. And how the algorithm works is it literally just picks the lowest priority number to schedule. If it yields or gives up the CPU or wants to go to sleep or anything like that, we just pick the lowest number. So we would break ties of the same process, of the same priority upon arrival order. And if a lower priority number becomes ready, we immediately switch to it. And then, like I said, we record how long each time each process executes for during this priority interval or time slice, however you want to say it. And then here, we would recalculate the priorities every 10 seconds, but the maximum time our process could run we might do round robin with that. So there could be the possibility that priority interval is different than the time slice the process gets, but we'll just assume that they're exactly the same right now. So every so often, timer interrupts still occur, so we keep control over the processes, we can preempt them and everything like that. So at the end of the priority interval, we update the priority of each process. It basically just decays. So we take its current priority, divide it by 2, and then add how long it ran for during that prime interval. And then to calculate the next slice, C is basically just keeping track of how long a process ran for in this interval. So whenever we recalculate the priorities, we reset everything back to 0. So how that would look like is, it might be a question like this. Assume all processes have an initial priority of 0, and then this is their arrival order. Since they all have the same priority, we have to run them in this order: X, then Y, then A, then B. So A and B, we'll call them CPU-bound processes. That means as soon as you schedule them, they want to consume CPU and only CPU. They wouldn't be trying to access files or anything like that, or do system calls, or block, or anything like that. We can assume X and Y are I/O-bound processes, and that means they are doing some operation that blocks, like they're trying to read from a file, read from a network, or anything that is slow. So we're assuming that if they're I/O-bound processes, when we run them, they make a system call, and then the kernel is going to essentially block them, let something else consume the CPU while it waits for some operation to happen. So in this case, we say that the I/O-bound processes, whenever we schedule them, they will execute for only 1 time unit and then block for 5. So that means they won't be eligible to run again for at least 5 time units. And in this case, hey, it might be accessing a file or something like that. So timer interrupts would still occur every 1 time unit just to make things easy. That's the unit we can preempt things. And each time slice in this case is 10, priority interval is 10. So what is the scheduling? So so if everything has a priority of 0, and then we arrive in X, Y, A, B, what do we run first? Yeah, X, right? So in this case, since X is one of the IO-bound processes, we can only run it for one time unit, right? So it runs from 0 to 1, and then it's blocked. So it can't run again for another 1, 2, 3, 4, 5. So it can't run again until time 6 here. So if they all have the same priority and X is now blocked, what do I run next? Y. So I run Y. It's another one of those IO-bound processes, so it only runs for one time unit, then it's blocked for 5. Now what do I run? A, right? So that is the last one that's eligible to run. At time 2, X is blocked, Y is blocked, so the next in line is A. So in this case, A runs until the next priority recalculation. So it actually runs for the next 8 time units, even though X is ready here. So X is ready at time 6, but it will not preempt process A because they have the same priority. So if they have the same priority, it will prefer to just not switch and just run whatever was already running. So if X came in and it had a lower priority, it would kick A out, but in this time they're all tied, so it wouldn't do anything. Yeah?
Why does X and A have the same priority?
So we just said that initially they all have the priority of 0. So we'll tweak it and see what the difference is. So at time 10 here, I have to go and recalculate all the priorities again. So process X, right, all of their initial priorities were 0, so 0 divided by 2 is 2. So basically their new priority is just going to be however long they ran for. So the new priority for X should be 1, new priority for Y should be 1, and new priority for A should be 8. So here, Y is ready, doesn't matter, and we recalculate the priorities for every single process. So everything started initially at 0, so 0 divided by 2 is 0, and then we just add however long they ran for in those 10 time units. So X1, Y1, A8, and of course B ran for nothing. So if these are the new priorities for the tasks, what are we going to run now? And lower is higher priority. Anyone? B, right? B is the lowest priority now of using our new priorities. Not a trick question, so we're just going to run B. Nothing else is the same priority of it. We don't really care. It runs for the next 10 time units. Everyone okay with that? All right, let's make it spicy. No, not really. Make it interesting. Probably not that interesting. So let's say processes A and B initially have a priority of 6, and the others, so X and Y, have a priority of 0. So we still assume the same arrival order all at time 0. Same rules apply. A and B are CPU bound. X and Y are IO bound. And same setup as before. So what are we going to run first this time? A. Wait, what? So what's the priority of A? 6. What's the priority of Y? 0. And lower number means higher priority, right? So we'd prefer to run X or Y over A, but we'd also prefer to run X above them all, right? Because it arrived first. X and Y have the same priority. X came first, so we would schedule X first. Everyone okay with that? All right, so now in this case, we schedule Y next, so X blocks. X will block for, those 5 time units, so we are not able to execute it. Next process is Y, runs for 1, and then it would block for 5 time units. Now, just like before, we can only pick between A and B. They both have the same priority of 6. So we would just pick A because it arrived first. So we would pick A, and in this case, it would only run for 4 time units because at time 6, that's when X is ready again. So in this scenario, since X has a much lower priority than A, it would immediately kick it out. So it would immediately kick it out and run for its 1 time unit and then block again for 5. Now, at time 7, Y is also ready. Y has a lower priority than, well, higher priority, lower number than A. So Y would run when it's ready, run for the 1 time unit and block for 5. Now what gets to run? A. So A would run until 2 time units, because at 10 we have to recalculate all of the priorities. Now this time I use the old priority number, right? My new priorities would be, well, X and Y had a priority of 0, so I just divide that by 2. That gives me 0, and then they each ran for 2 time units. So their new priority would be 2. And in this case, the priority of A, well, it started off at 6. We divide it by 2, and it also ran for 6 time units. So its new priority is 9. And then for process B, its priority was 6. So divide by 2, and then it ran for 0 time units, so its new priority is now 3. So now here's the tricky part. At time 10, what do we schedule to run? B, right? Because X and Y are both blocked at that point. 1, 2, 3, 4. So X isn't ready until this time here. So we would actually run, 12. So we would only run B for 1, 2, 3, 4, 5. Yeah, okay, sorry. So we run B for 2 time units, and then at 12, that's when X becomes ready again. X still has a lower priority, or higher priority, lower number than B, so it's going to kick B out, right? So it's going to kick B out. We're going to run X for 1 time unit. Then Y is ready. Oh, okay, well, Y is ready. It has a lower number, higher priority than B, so we would prefer to schedule Y. And then at this point, both X and Y are blocked, so we're back to just picking B. It would run for 4 time units until eventually X is ready again, still lower priority, we haven't recalculated it. X runs, then Y runs. Joy, wasn't that fun? So you could do this if I asked you to, right? So scheduling, yay. Any questions about scheduling or anything like that? Yeah?
What if the timer interrupts occurs every 1 and each time slide is 10 here?
So that means like it kind of acts like round robin. So if for some reason, whenever we recalculated here and process A was still running, process A would at most run for 10 time units by itself until it tries to pick anything else, but it would probably pick itself again and just keep on running, so it doesn't really matter.
And so what if the time interrupts occurs every 1, like every 1 time slice a timer interrupts?
So timer interrupts occur every 1 just means that I can only kick a process out every time unit.
You have to run the full time slice. You cannot like switch.
Yeah, I can't switch in like half time units just to make it easier to calculate. Yeah.
So the priorities are only calculated at the like priority intervals and
Yep.
when the like CPU bound processes exit, right? Those are the 2 cases when you calculate.
No, you only recalculate the priority in this case every 10 time units, and that's it.
Okay, because when A ends, right, you're at 10, and then 10, like the priority is not, the interval's not over yet.
So
When they recalculated there.
So at 10, that's when we would recalculate everything.
Yeah, but that's not the end of the fucking interval.
Yeah, so priority interval, it just starts at 0 and then it's every 10, no matter what. So it just recalculates every 10 time units. Yeah?
Sorry, do you mind re-explaining the difference between time slice and priority interval? Like they have the same number here, but why is time slice?
So time slice would be like the most one process can run for before the scheduling algorithm runs again. In this case, it's not going to matter because it's probably the same priority. Like, it's not going to matter in this case. It's kind of like an implementation detail. It doesn't actually matter, but like the scheduling algorithm would kind of be round robin, and then every so often we'd also recalculate priorities. And then if something has a lower priority now, then we'd kick whatever's currently running out. Yeah.
Okay, so back to my question. Were the priorities recalculated at 6? Because at the point at 6, like the priority interval was not over yet.
No, they were not recalculated at 6. So at 6, we were using the same priorities before. The only difference was at 6, we said x is IO bound, so if it executes for 1, it's blocked for 5 here. So right now, x is blocked, 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 and then x can run again at time 6. And then it kicked A out because it has a higher priority or a lower number.
Okay.
But we didn't recalculate everything, so we were using these numbers. So x had a priority of 0, and at that time, A had a priority of 6. So x had a lower number, so we kicked A out immediately whenever it wanted to execute again. All right, any other questions? Scheduling, fun. All right, so I'll show you some magic now. So let's see if this link works. So LLMs, yeah, kind of a cool topic, right? So 30 billion parameters of an LLM, that's like lots and lots and lots of memory. Like, I forget, how much is that? Like 32 gigs or something like that? But someone made this magical commit to one of the libraries that actually uses LLMs in just a single line change. They changed the code from actually using 32 gigs of memory to only using 6.8 gigs of memory. And someone thought they were an absolute wizard, but we can actually figure out what was going on. So if I do this, can I make this any bigger? I don't know if I can make it any bigger. But yeah, there's a link to this. There's a lot of discussion here of like, hey, what the hell is going on? How do you do this magic? Whoops, I exited my slides. That's not good. So we are going to figure out what is actually going on here. So in order to start unraveling this mystery, we get to learn a new system call. So we can actually control our process's virtual memory. So there is a system call called memory map or mmap because of course we want smaller function names. Naming it memory map would be way too long. And that is a way for you to control your own virtual memory in your process. So the pointer you get back is of course a virtual address, and using this system call, you can actually set it up so that a virtual page, instead of just mapping to a physical page in memory, you can set it up so that it actually maps to a file instead. So if you try and access that memory, instead of the operating system allocating a new page for you that has no data on it, it grabs a new page for you and then copies the information from the file instead of just getting random bytes. So you can actually use this to read and write a file without any of those pesky read and write system calls, which is kind of neat. So the way mmap works, we'll see an example, but it is a function that takes a almost confusing amount of arguments. It takes 6 arguments. So the first argument is a pointer to an address, well, just an address. And you can actually say, hey, kernel, I want to start at this exact virtual address, set up the mapping for this exact virtual address. You can also pass null if you don't actually care what specific virtual address you get returned. Then the length, the number of bytes to map. Then some protection flags that should look familiar to you, that looks like, you know, the bits on a page table entry. So whether or not I can read, write, or execute a page. So you can imagine how this is implemented. Then some flags, so mapping flags. So shared means that I can, when I fork, this virtual mapping is actually the same in the parent and the child. And that way you can actually share memory between 2 processes and do inter-process communication without any system calls. So that is a very quick way to do inter-process communication. Or you can set it up as private, and private will ensure that even if you fork, the forked process will be independent from your process, so everything is independent again. And then you can also say anonymous, and that just means the mapping's not backed by a file. So the fifth argument here is a file descriptor. If you just want anonymous memory, you don't want it initialized with the contents of a file, you can just ignore it. But otherwise, it's the file descriptor that you want to start reading data from and populating all of those virtual pages with. And then the third one is an offset, so that's the offset, how many bytes to start the mapping from, which must be a multiple of the page size. So let's just see an example, because this is actually a fast way to write a file, or an easy way to access a file. Virtual machine. So, yeah, so before this, how you would read the whole contents of a file. Anyone describe to me how you would read every single byte in a file before knowing about this? We kind of did it before. Yeah.
You open it and then you read into a buffer until end of file, and then you close it out.
Yeah, you would just open the file and then do however many read calls into a buffer until eventually read returns 0, and that means you've read everything. But you would only fill a buffer at a time. Who knows how many times you have to call read? Can you fit the whole file in memory? Is your buffer big enough for the file? Do you really want to deal with parts of a file? You've got a whole bunch of questions there, right? It's kind of annoying if you actually need to read a really big file. So you can actually use memory map to make this a whole lot easier. So instead, we still need to open a file, so we'll be meta and open this file. So we'll open this file itself. We'll open it for read only. We'll just make sure that we get the file descriptor. So just review, by default, each process should have file descriptor 0, 1, and 2, standard in, standard out, standard error. So this is just Sandy checking for me. So the next available one should be 3. Then there is a stat structure, so that's a struct that will actually tell you information about a file. So if we call the system call fstat, give it a file descriptor and an address to stat, it will go ahead and populate it for us. And some things it will tell us about the file that we care about here is the size of the file. So using that, we can mmap it. So first argument, we don't care where it goes. Second one, the length of the mapping is going to be, we want to map the entire file into memory. Then we're just going to say, hey, we only want to read it. And then we'll just say, hey, we just want to be private only for this process. Then we want the initial data to come from the file descriptor, not anonymous memory. And then offset 0, so we just want to start at the beginning. So after we do this, we get a pointer back, right? Just a pointer to the start of the mapping. So here I'll just read characters from the file. So here we can error check, make sure if mmap fails, it returns map failed, which is basically a null pointer. And then we can close the file descriptor because now we don't need to use it through the file descriptor. We used it so that we can tell the kernel that, hey, I want to actually map the file using these virtual addresses. So we can probably guess this mmap would be modifying the page table entries, as many pages as it needs for the file, and essentially mapping the first one to the first page of the file, second one to the second page of the file. And how this works is as soon as we access it, then it will actually read from the file for us. So if we want to read the contents of the file, instead of having read system calls now, we just treat it as a big old array now. So we can just iterate over every single byte of the file and just print out the characters. And this should just print out the entire contents of the file, right? And then for mmap, it's kind of like malloc, you have to free. So the equivalent of free for mmap is unmap. So if we run this, we see the contents of the file. No pesky read system calls or anything like that. And it's really, really efficient. So how it kind of works is, well, it returns, some new virtual pages for you. So let's say we have 2 entries. Say that my file is big enough for 2 blocks. So here would be like physical page. I don't know, give it a number. Give it a number. So what's actually happening here is that initially, like if you've kind of started doing copy on write, it would set up this, it would essentially set up this page table entry that's supposed to map to, this should be like the first, first page bytes of the file, right? So it should map for the first page bytes of the file. How the kernel actually implements this is it will just set the valid bit equal to 0, and then essentially write a bunch of bookkeeping information in the rest of the page table entry that keeps track of what file and which page this entry should represent. So similarly to the copy on write, whenever you try to first access the first byte of the file, you'll get a page fault, right? So in this scenario, you will get a page fault, and then the kernel, like your copy on write stuff, will be like, oh, no, wait, I can fix this. So then it will read the first page of memory from the file. Let's say this is the whole file. Say it only consumes 2 blocks. So let's say we have a file that spans 2 blocks somewhere on a disk or something like that. So page fault would happen, and then the kernel would be like, oh, okay, I can fix this. So I copy all the data. Let's say it starts with like an include or something like that. I would copy all of the data onto this page, this physical page, and then just set the valid bit to 1. Now it's a valid mapping. It actually has all of the data, and then set the rest of the entries based off of the permissions you set. So like now it's readable or something like that. And then the next, 4,095 bytes I read from the file doesn't actually have to access the file system or anything like that until I read the next byte that would start on the next page, and then transparently it would page fault in the kernel. It would go ahead, fix up, populate the physical page, grab a physical page, copy all the data from the file, fix up the page table entry, and then just carry on over and over again. So it doesn't matter how big your file is, it'll just keep on doing this. And the nice thing about this is even if I map a file that was say I map a file that is 4 blocks big, which would take 4 different entries. If I never access, one of these 2 blocks, then it will actually never copy all that data from the file and bring it into memory, and it won't actually use any memory. So essentially when you mmap, no pages get allocated for you. It just sets up the page table to keep track of everything, and it will only grab physical memory whenever you try and use that memory. Yeah?
So who's keeping track of knowing which block of the file maps to which physical page?
The kernel keeps track of which block of the file maps to what. Yeah. All right, cool, huh? So, much easier way to read a file, ain't it? And less system calls, stuff just transparently reads from the file for you. Kind of neat. Any questions about this thing or anything you want to try with it? Yeah?
If you pass it anonymous, is mmap just essentially the same as malloc?
Yeah, if you pass it anonymous, it's essentially the same as malloc, except little difference. Malloc will use the heap, and this can be anywhere. So sometimes spoiler alert, if you're implementing malloc yourself and you ask malloc for a large piece of memory, it will not allocate it on the heap, it will mmap it. And it will mmap with anonymous because that's just way easier than using the heap. So some memory allocators might actually just use mmap instead of the heap. Neat. So here, I could try and modify it too. What is that? Oh, whoops. So I could try and modify it, run it. Hey, segmentation fault. Uh-oh. Why'd that happen? Well, what was the protection here? It's supposed to be read-only, right? So if I try to write to it, like exactly, you probably haven't seen read-only things before, but there is such a thing as read-only memory, and they will seg fault. So like, has anyone tried to modify like a string literal and it seg faulted and you don't know why? Just me? Okay. Well, you can try this yourself and see if you have a string literal and you try to modify it, it seg faults. It's not because the address isn't valid, it's because all of your global variables they're all read-only strings, they're all in read-only memory, so if you try to modify it, you get a seg fault even though you're not using invalid memory, you're using memory invalidly. So, any other fun things you want me to break here? No, we're not terribly fun today. So if I wanted to, I can do other fun things. I could open it, I could let myself modify it, right? So I could put a write flag on there, so now I can actually modify the memory. So now if I run this, well, here I read the contents of the file because I read it first before I modify it. Now, if I kept on updating it over and over and over again, one question you might have is like, hey, did I just fill my file full of A's? So if I look at the actual file, VS Code doesn't immediately refresh it. If I look at this file, is it going to be full of A's? Yes? No. So turns out that if you ask for private, so here are these protection flags. If you ask for private, that means only in this process, even if I modify the contents of it, I won't actually change the file. I won't actually affect anything else. But if I wanted to, I could do it shared. And then this will effectively bring this example to a close. So now if I have it as shared, now when I modify it, it's actually going to modify the file as well. So now when I run this, again, I print it out, but if I look at it, it's not full of A's. Uh-oh. Oh, right. So this time, it failed for a different reason. So the original file I opened was read-only. So I didn't get an error, and I saved myself a little bit. So I actually also have to open this for, what is it? So I'll open it for reading and writing. So now I should brick it. Geez, sometimes it's really hard to cause yourself an error. So now if I run it, now I get the content back out. That makes sense because I read it before I wrote to it. But now if I write to it, it's full of A's. So I didn't have to do any write system calls or anything like that, right? Much easier than read and write. mmap, learning about virtual memory, actually good. And it's like, oh no, I just ruined this example. Well, I mean, we have git, so git restore. No harm, no foul, it's back. So, based off that, yeah, a few other things to note. mmap, it's lazy, like I said before. why I explained how it worked. It just sets up page tables, it just sets up entries, doesn't actually read the file until you actually use it. Like I said, it just creates an invalid PTE with some bookkeeping information to figure out that if you actually try to use this virtual memory address, how should I populate the data for the page when I grab a new one? So the remaining bits can be for bookkeeping. Where on disk is this entry? It's basically got, like, the valid bit's only 1, so it has 63 bits to play with. So you can see how they format it, but it's really not that important. Big thing to know is first access, that generates a page fault. The kernel then reads the file into memory only at that point and gets the page. And this ensures only parts of the file that get read actually get brought into memory. So back to this big question. For this LLM, yeah, the model was 20 gigs. The implementation before that did write system calls over and over and over again to finally fill 20 gigs of memory. But somehow they made use of this entire 20 gig model while only using 6.8 gigs of memory on a real system. So whenever you do model inference, typically models are like really sparse when you do inference, so you don't use all of the model. So what did they likely do to get such a improvement on memory usage? No big guesses? Yeah, they mmap the entire model instead of reading it. And that way, not only is it easier than reading it several times, it's also much more efficient. So it would only load into memory the parts of the model that actually get used for free. You don't have to do any silly checking or anything like that. So that's all they did. That one thing that someone said they were some type of wizard and did the impossible, all the person did was delete a whole bunch of things and put one mmap call in there. So you too can be a wizard with the help of this course. So we can actually kind of argue about it. So, So just by doing the mmap call, we should be able to figure out that if we had like a, that's a highlighter. If we had a 20 gigabyte model, how many PTEs need to be modified? Modified slash added. Added's probably a better word. So how would we even begin to figure this out? Yeah. Yeah, find out first how many different pages does that 20 gigabytes take, because that's how many entries I need in my L0 table, right? Because they actually do the final mapping. So I need to divide this up into pages, and figure out how many pages I need. So 20 gigabytes is the same as 20 to the power times 2 to the power of 30, because that is 1 gigabyte. And then divide by the size of a page, which should be 2 to the 12, right? So that means we need 20 times 2 to the 18 pages, which is AKA same as the number of PTEs, right? In L0. Right, everyone agree with that? All right, so is that all we need? So in total, let's see, if I crunch the numbers and figure out that, hey, this is how many pages I need, how many page table entries I need, then I can divide them by however many entries I can fit on a page, right? So this is how many entries on a page, which means that I would have 20 times 2 to the 9, essentially full L0 page tables, right? Everyone kind of agree with that? So this is something like 1,240 full L0 page tables. So is that all the extra memory that would get used for doing that mapping for that 20 gig file? Yeah.
You probably need to touch some L1 page tables because there's too many L0 page tables.
Yeah, so if I have this many full L0 page tables, well, I need some L1 page tables to point to them, right? Which probably don't exist anywhere. So also this gets to being pedantic because this is like, hey, how much extra memory is required to keep track of the mapping? It's at least 40 gigs, but realistically, right, we need some L1 page tables so we can point to these ones. So how many L1 page tables do we need? Well, essentially, we just have that 10,240, and then divided by 512. That's how many entries we can fit per L1 page table, or just how many entries in a page table in general. And if we crunch that number, it is 20, which kind of makes sense because, well, if we draw out our virtual address, right, on the normal scheme, 12 bits, 9 bits, 9 bits. So basically, the L1 and L0, if we just consider them, they're like 30 bits of the virtual address, which is just a gigabyte, right? So if they were all full, well, each full L1 page table essentially maps an entire gigabyte. Makes sense. And also makes sense, you know, if we had every entry in L0 full, that would be 512 gigabytes, which would be all of our memory. So makes sense. So technically the total usage that we use in this mmap call would be 40 megabytes for the L0 page tables, plus these 20 full L1 page tables, and each one of them take up, you know, a page. And of course, each one take up a page. And then being super pedantic, if you calculate it, it's like actually we take up 40.07 megabytes of memory for the mmap call to map everything. That includes the L0 and the L1 page tables. Why did we go through all that to be correct? I don't know. Doesn't really matter. First approximation, just keeping track of the L0s is all you really need. Yeah?
How do we find a page size, like the 2 to 12?
2 to the 12 is just, every x86 will be 4 kilobytes. Fun story, if you have Apple Silicon, you're using it on your phone or your tablet or your laptop, your page size is actually 16 kilobytes. Neat. That has some implications, right? If your page table has the same number of entries, what's good about having a 16K page instead of a 4K? Well, if your cache is only 10 entries, you cover 4 times as much memory than those people on x86. So you Apple people can be smug that your page size is bigger. Fun. All right, any other questions?